Iceland's starting plume. Again, the plume was centered underneath Greenland. We had the plume material pond beneath the continent. You could between Scandinavia and Greenland. The extensional basin here in the Irish Sea. If you go from London towards Oxford and farther to the west, you're going in deeper and deeper into the structure. The Irish Sea is a structural high. The Thames flows, and the other rivers in Ireland and Britain flow radially from the Irish Sea. This is uplift. The reason it's a valley is the rocks in it are relatively easily eroded. And we have plume material that got closed lithosphere coordinates got trapped here. When the seafloor spreading started here, we had thin lithosphere. The North Sea had been uplifted, and plume material that was trapped beneath the North Sea was able to fall out and go into the Atlantic basin. So there's this will complicate the uplifts science history of the North Sea at the time the plume comes in. That will uplift, will get downdrop when the spreading occurs, but some heat will have been added here, so there'll be enough net uplift. Okay, and again, just trying to reiterate this, we have plume material not trapped freely, drain out from the North Sea into the new ocean basin, and this is another complicated way to produce vertical tectonics that's, again, not particularly well understood or well applied in geology. We also get features here with the East Antarctic plume flying to seamounts here when the seafloor spreading first starts here between Australia and Antarctica, and there are seamounts here that predate the previous activity. The passage here of deep water has climate effects, and there are plume material being trapped in rip basins here. Off the diagram is following a rip basin. Here, some of it getting trapped. Again, complicates the geology of this part of the world. Michigan Basin will shift here. It's the classical interior basin. The Moscow Basin is another example closer to here. It subsided in the Paleozoic. In this case, there's no obvious plume and rifted effect. North America is surrounded by rift margins, so Michigan is not as interior as it was now, but it's still quite a few hundred kilometers from the nearest margin. I've got to point out that the substance of a basin with plume material in it behaves differently than the classic Mackenzie model of stretched lithosphere. Older models of basins just simply put in boundary conditions for convenience, and I'm going to take advantage of the physics of small-scale convection. Again, there's a map of Michigan. The lakes here are where the salt outcrops, there are erosional salt basins. This is a much older rift basin. It's about 1,100 million years old. And the lower lakes off here are early Paleozoic Eocambrian rift basins. And the sediments and also the depth that sediments are deposited increases to the center of the basin. This is like Hall's classical myogeosyncline, that the material was relatively near sea level during its entire history, and the land subsided as the basin was deposited. Cross-section here, some later tectonics from the Appalachian collision. Again, we have young sediments at the center, then some erosion off the top, salt outcrops troughs on the two sides of the basin, and hence the Great Lakes. Salt erodes well. We have very rapid subsidence, and then possibly a tail of sedimentation here. And just like you crudely expect, and I turned the substance so it looks like a mid-ridge substance, rather than the way I did in my mid-spec view. And the conductive heat flow through the lithosphere is proportional to lithospheric thickness. Inversely proportional thick lithosphere. The convective heat flow, when you're at long time scales to the square of the lithospheric thickness, convection becomes stronger as the basin subsides. Conduction becomes weaker. Eventually, we converge gradually to an equilibrium. The sedimentation, if we do a model simply with small-scale convection in, varying the final lithospheric thickness, we end up getting a relatively poor fit to the observations. And get the subsidence steep at first, we end up with far too much subsidence. If we fit the total amount of subsidence, we don't get the steep subsidence that occurs early in the history of the basin, and we don't get the long gradual tail. So we put plume material in here, and the key with plume material is the bottom of the plume material is stably stratified. This is a numerical model again. Plume material gradually cools. It takes a good while to cool. Heat is escaping from the top. No new heat is coming from below because this is a stable base. There's no convection to bring heat up to the model. So the full heat loss to the top ends up causing subsidence. We get very rapid subsidence. And if we model this, we get a much better fit. Any of the deviations here correspond with the deviations from so-called eustatic effects on the North American model. The center of the basin here is isolated at times of low sea level. It can continue to subside in this extremely arid climate that existed in Michigan at the time. It's much like closed basins in the center of the outback of Australia. You don't get much deposition, you don't get much erosion, and then the basin fills with salt in the Silurian when the sea level comes back up, the glaciers melt, and we fill the basin with salt. Okay, just quickly add here this lateral flow of material. Plumes are sources of top material which cut off, they're complex. You have this lateral flow. You also have the difficulty of imaging seismically the deep amount of plumes. There's the mantle wind, they're complicated. Plumes can get cut off by slabs like the Yellowstone plume and then appear to restart again. Even with Hawaii, we have this Hawaiian swell from lateral flow, which becomes is somewhat complicated, but ends up in this case being simple enough it's giving us signal. We have hotspot tracks here. We have many weak features, and skeptics still need to demand deep evidence for a deep process. Plumes explain so many things reasonably well, other things passably well, that it's a viable hypothesis and meets the criteria. We shouldn't regard it as infallible. We're out here seeing the plume in action and seeing lava flows and rocks younger than many of the people in this room, including Alice and myself. Thank you.